Welcome to Olympiad Math for Year 5. This is Lesson 4, we'll learn solving problems by forming systems of equations. In this lesson, we will learn and understand how to solve real-world problems by forming systems of equations. Master techniques such as elimination and substitution, and learn to apply them flexibly. We have previously learned how to solve real-world problems using the idea of setting up equations. In this lesson, we will explore how to solve problems by forming and solving systems of equations. A system of equations refers to a set of two or more equations that involve unknowns. Generally, if a problem involves two unknowns, we need two equations to find a unique solution. If there are three unknowns, then we need three equations to determine the solution uniquely. The key idea in solving systems of equations is to reduce the problem from multiple unknowns to a single unknown, and then solve it. The two common methods for doing this are: substitution method, express one unknown in terms of the other using a relationship given in the problem, then substitute this expression into the other equation to form an equation with only one unknown. Elimination method, add or subtract the two equations so that one of the unknowns is eliminated, leaving an equation with just one unknown to solve. Example 1, Mother Squirrel collects pine nuts. On sunny days, she can collect 20 pine nuts per day, and on rainy days, she can collect 12 per day. Over several consecutive days, she collected 112 pine nuts in total, averaging 14 per day. How many of those days were rainy? According to the problem, the pine nuts collected by Mother Squirrel include those collected on sunny days and those on rainy days. The total number of pine nuts collected is known, and the number of days used to collect them is also fixed. Therefore, this problem can be solved by forming a system of equations. Let the number of sunny days be x, and the number of rainy days be y. Then we will have equation 1 and 2. Simplifying 1 gives equation 3. If we use the substitution method to eliminate an unknown, from equation 2, we can get equation 4. Substitute equation 4 into equation 3, we can find x equals 2. Then, we can find the number of rainy days is 112 divided by 14 minus 2 equals 6 days, or substitute x equals 2 into equation 4 to get y equals 6. Alternatively, from equation 2, we can write x in terms of y, giving x equals 112 divided by 14 minus y, which we'll call equation 5. Substitute equation 5 into equation 3, we get equation 6. Then we solve to get y equals 6. Clearly, substituting equation 5 into equation 3 directly gives the answer, 6 rainy days. If we use the elimination method to eliminate an unknown, we multiply equation 2 by 5 and subtract equation 3, then we get y equals 6. It seems that, for this problem, solving the system of equations using the elimination method is simpler. The answer is there were 6 rainy days. In fact, the substitution method and the elimination method are essentially the same. The elimination method simply skips the substitution step, making the solution more concise. But whether the elimination method is always simpler depends on the specific problem. Example 2. Two people, M and N, set off at the same time from two places 60 kilometers apart, walking toward each other along the same road. After 6 hours, they meet somewhere along the way. If each of them increases their walking speed by 1 kilometer per hour, then the new meeting point is 1 kilometer away from the previous one. Find the original speeds of M and N. To visualize the problem more clearly, we can use the following diagram. Let x be m's original speed in kilometers per hour, and y be n's original speed in kilometers per hour. According to the condition of the first meeting, we can get x plus y equals 10. So the original combined speed of m and n was 10 km per hour. At the second meeting, m's distance may be either 1 km less or 1 km more than what it was the first time, that is, 6x minus 1 km or 6x plus 1 km. The time taken for the second meeting is 5 hours, so ms total distance in the second case is 5 times the sum of x plus 1. From this, we can set up a system of equations based on their total speed and m's walking distance. From equation 2, we can get x equals 6. Substitute x equals 6 into equation 1, we get y equals 4. Alternatively, if we use the other case to set up the system of equations. From equation 4, we get x equals 4. Substitute x equals 4 into equation 3, y equals 6. The answer is the speeds of m and n are 6 km per hour and 4 km per hour, respectively. From example 2, we see that the person with the faster speed ends up walking a shorter distance during the second meeting. This relationship isn't easy to determine at the beginning, which is why it's important to consider both possibilities at first. Example 3, there are 150 soldiers who need to reach a location 90 km away to carry out a mission. It is known that they can march quickly at a speed of 10 km per hour on foot. There is one truck available, which can carry 50 people at a time and travels at a speed of 70 km per hour. Please design a plan for transporting and walking that will allow all 150 people to reach the destination in the shortest possible time. According to the problem, the only way to minimize the total time is for both people and the truck to keep moving toward the destination without stopping, and for the truck to keep making trips back and forth, continuously transporting people, until finally all 150 people and the truck arrive at the same time. From the given conditions, the 150 people must be divided into 3 groups of 50, with each group assigned a plan of riding and walking. As shown in the diagram, solid lines represent the truck's round trips, and dashed lines represent the walking routes. Clearly, for all 3 groups to arrive at the same time, the riding and walking distances for each group must be the same. Let the riding distance per group be x kilometers, and the walking distance be 2y kilometers. Then we can have equation 1. Also, the time the truck takes to carry the first group forward and return to pick up the second group is equal to the time the second group walks. So we have the equation, then simplifying gives equation 2. Substitute equation 2 into equation 1, we get y equals 15. Substitute y equals 15 into equation 1, we can find x equals 60. So, the shortest total time for all 150 people to reach the destination is 3 6/7 hours. The answer is the plan is to divide the 150 people into 3 groups of 50. Each group rides the truck for 60 kilometers, then walks the remaining 30 kilometers. All 3 groups depart at the same time, follow this segmented riding and walking route, and arrive together in exactly 3 6/7 hours, which is the shortest possible time. Example 4, table below shows the scores of 40 students in a math competition. If the average score of the class is 2.5, how many students scored 3 points and how many scored 5 points? According to the problem, we just need to let the number of students who scored 3 points and 5 points be unknowns, and then use the total number of students and total score to form a system of equations. Now, try setting up and solving the equations on your own. The answer is there are 7 students who scored 3 points, and 4 students who scored 5 points. Now, check your answer, is it correct? Example 5, A school purchases some sports equipment at unit prices of $200, $300, and $400 respectively. The number of $300 items is twice the number of $400 items, and the number of $200 items is one more than the total number of $300 and $400 items combined. If the total cost for all three types of equipment is $9,800, how many items of each type were purchased? According to the problem, we are given the following three relationships. The number of $300 items is twice the number of $400 items. The number of $200 items is equal to the number of $300 plus $400 items, plus 1. The total cost of all items is $9,800. So we can set up three unknowns and solve the problem using a system of equations. Let the number of $200, $300, and $400 items be x, y, and z, respectively. Then we can have three equations. This is a system of equations with three unknowns. Simplifying equation 3 by dividing all terms by 100 gives us equation 4. Following the elimination method introduced earlier, we can first eliminate one unknown. Substitute equation 2 into equation 4 to eliminate x. After simplifying, we have equation 5. Now the system is reduced to two equations with two unknowns. Substitute equation 1 into equation 5 to eliminate y, we can get z equals 6. Substitute z equals 6 into equation 1, we can get y equals 12. Substitute y equals 12 and z equals 6 into equation 2, we can get x equals 19. Thus, the solution to the system is x equals 19, y equals 12, z equals 6. The answer is the school bought 19 items at $200, 12 items at $300, and 6 items at $400. Example 5 involves a system of three equations. To solve such systems, we can still apply methods for solving two-variable systems by eliminating one unknown first, reducing the system to two equations with two unknowns, and then further reducing to a single equation with one unknown in order to solve. Example 6, there are red, white, and black balls. The total number of red and white balls together is 25. The total number of white and black balls together is 31. The total number of red and black balls together is 28. How many balls of each color are there? The problem gives us the pairwise sums of the three types of balls. So as long as we assign variables to represent the number of each type of ball, we can form a system of equations and solve it. Let the number of red balls be x, white balls be y, and black balls be z. Then we can have a system of three equations. If we follow the basic method used in earlier examples, subtract equation 1 from equation 2 to eliminate y, after simplifying we can have equation 4. Now use equations 3 and equation 4 to form a system with two unknowns x and z. Add equation 3 and equation 4, we can solve z equals 17. Then we can have x equals 11 and y equals 14. We can also solve this problem using a more flexible approach by recognizing that the sum of all three variables can be found directly. Add equations 1, 2, and 3, after simplifying we get equation 5. Now subtract each original equation from equation 5. From equation 5 minus equation 1, we get z equals 17. From equation 5 minus equation 2, we get x equals 11. From equation 5 minus equation 3, we get y equals 14. This example shows once again that understanding the problem structure and making full use of the given relationships can not only help reinforce basic methods like elimination, but also improve problem-solving efficiency through flexible strategies. Example 7, 3 students, A, B, and C, took a long-distance bus trip together. Each of them carried luggage that exceeded the free weight allowance and had to pay an extra luggage fee. A paid $0.5, B paid $1.5, and C paid $2.5. The total weight of the 3 people's luggage was 120 kilograms. If the entire 120 kilograms of luggage had been carried by one person, the fee would have been $9.5. How much luggage did each person carry? According to the problem, the free luggage allowance per person, each student's actual luggage weight, and the fee per kilogram of excess weight are all unknown. To clearly and fully express the quantitative relationships, we can represent all these unknowns using variables. Let A be the free luggage allowance per person, B be the fee per kg of excess luggage. Person A carried A plus X kilograms of luggage, person B carried A plus Y kilograms of luggage, person C carried A plus Z kilograms of luggage. Then the following equations can be established. In equation 5, the expression of 2A and X and Y and Z represents the excess luggage weight if one person carried all the luggage. Now substitute equation 4 into equation 5, we express B in terms of A. From equations 1, 2, and 3, we can express the excess weights as equation 7, 8, and 9. Substitute equation 7, 8, and 9 into equation 4, after simplifying we express A in terms of B, and label this as equation 10. Now substitute equation 6 into equation 10, after simplifying we get A equals 25. Now substitute A equals 25 into equation 6, we can get B equals 0.1, finally, substitute A equals 25, B equals 0.1 into equation 7, 8, and 9, we can find the value of X, Y, Z. So the answer is A carried 30 kilograms, B carried 40 kilograms, and C carried 50 kilograms. Here are the practice problems for today. Thank you for watching and hope you enjoy your math today.